Hello, I'm going to be answering a question that is in Chem Activity 17 in the exercises on page 319. There is this question, number 3. It says, consider the following representations of butadiene. So we can see 3 different representations there. And on the far right, we see a representation that shows some dotted lines. So I'm going to use my highlighter pen here and hopefully, oops, that doesn't look like a highlighter pen. I'll erase that. Trying to use yellow. Yeah, okay, so these dotted lines right here. It says each thin dotted line, so the ones I just highlighted, on the furthest right representation of 1,3-butadiene above represents approximately, and we're supposed to choose, is it a little less than 1 double bond, over 100 kilocalories per mole, or a little less than 1 pi bond, like 64 kilocalories per mole, or a little less than half of a pi bond, approximately 32 kilocalories, or 3% of 1 pi bond, approximately 2 kilocalories per mole. Well, if we go back to the first page of this chem activity, and let's see if we can get there. Here we go. The first page of this chem activity is on page 312. It's about first part is about conjugation. So if we look on the right, we can see, again, we have 1,3-butadiene, and 1,3-butadiene shows this single bond between the 2 double bonds. It says, what is the length of this bond compared to an ordinary single bond? Well, it's actually shorter, and the reason it's shorter is because it has partial double bond character. We have some full double bonds here, and then we have a little bit of electron density that's between those 2 double bonds, and that's these conjugated areas. The conjugated pi bonds share some electron density. Well, how much electron density do they share? Is that like a full double bond in between? It's not. So let's look at the next section. It talks about these 1,3-butadiene. It says that the conjugation of the 2 double bonds in 1,3-butadiene creates 2 conformations that are separated by a small activation barrier. So we have the trans-like 1,3-butadiene, and we have the cis-like. And it says that they can be rotated around that single bond, which isn't truly single bond. It has some double bond character, and the activation barrier to get from the cis-like to the trans-like is 4 kilocalories per mole. Now, it says a regular double bond on the right side of this. It says, for comparison, a regular double bond we cannot rotate because the activation barrier is 60 kilocalories per mole. Well, 60 is a lot bigger than only 4. So if we go back to the question again, exercise 3, it asks about this little bit of electron density that I've highlighted that gives that single bond partial double bond character. So remember that it was, if we scroll back over, the activation barrier for that single bond that has partial double bond character was about 4 kilocalories per mole. So remember that both of those added together are about 4 kilocalories per mole. So when it says, it says each thin dotted line then represents half of 4, which is about 2, which would be the third or the fourth answer, approximately 2 kilocalories per mole. So that's only about 3% of 1 pi bond. So we also have to remember that the regular pi bond here is actually sending some of its electron density over, and so part B says each thick dotted line on the furthest right representation of the 1,3-butadiene represents approximately, and it's going to be, remember the whole pi bond is both sides added together, so 1 is going to be half of a pi bond, and it's actually going to be a little bit less than half of a pi bond because the electrons are going over in between the two pi bonds. So it's going to be a little bit less than half of a pi bond. So since a pi bond is 60, each one of these is going to be 30. And so a little less than half of a pi bond, approximately 30 kilocals per mole, would be the answer for part B. And that is the end of this explanation.